All right, well, welcome to the last calculus class of February. Believe it or not, we're at the end of the month here. So the plan today, of course, as always, after we go over any kind of homework questions or anything else you guys have, we're going to keep talking about trig integrals. So we started last time looking at how we deal with integrals of sine and cosine when we've got odd powers. Today we'll start with what do we do when we've got only even powers. And then we'll turn our attention to other forms, like what if we have secant and tangent? What if we've got, mixed angles, some things like that. And then we should be able to start into what's called trig substitution, which is taking other forms and substituting in trig functions. So all kinds of trig today. We're going to see all kinds of identities that you probably have forgotten. And things like that. So we are not having 2 quizzes next week. You guys need to bear with me a little bit with the dates of everything on Canvas. I know that, like, I got a message yesterday about, well, wait, are we still having a quiz tomorrow? And I hadn't changed in Canvas. No, I hadn't dealt with that. And I changed the dates on that, and now it looks like there's 2. Just be patient. I'll get everything fixed up. It takes me a while to deal with all this stuff. So no, we are not having 2 quizzes next week. We're only having 1 quiz next week. I just haven't had a chance to change everything. Okay. So, but no, we're not having 2 quizzes next week. Anyway, so my plan is to do all kinds of trig stuff today, but let's start with questions you guys have, homework and otherwise. So, all right, what do we got? All kinds coming out. So 3.1, let's see, we got 6, 12, 13, and 14, and 3.2, number 13. Thank you, Susanna and Alexi. Any others to put on the list? Was there anything in particular, Rigney, about number 10?
I just, I was having some difficulty integrating the function that I wound up with. Or at least I didn't think I was having difficulty, but I got the wrong answer.
Okay. Then I'll go ahead and put it on the list. We'll at least get them started, all of these. So, all right, anything else? Okay, so let me go ahead and share my screen and we'll go take a look at those. All right, so we'll start with the ones from 3.1. Good little integration by parts. All right, so the first question was about number 6. All right, so we've got natural log of x over x to the 8th. And we're integrating from 1 to 2. All right, so let's go ahead and go to whiteboard. And let's see what we're going to do here. All right, so 1 to 2, natural log of x over x to the 8th. All right, so they suggest using integration by parts, and I definitely agree. So the question is, what are we going to use as our u and what are we going to use as our dv? All right, well, we've got that little mnemonic, right? Liate. So our choice for u, since there's a natural log, that's probably a good place to start. So let's try u equaling natural log. So the dv is going to be dx over x to the 8th. All right, so once you pick your u, just everything else goes into the dv. All right, so then the process, we need a du. So we differentiate natural log, we get 1 over x dx. And then we need to integrate v. All right, well, I think that's x to the minus 8. Whoops, the dx is not an exponent. So if we integrate that, we add 1 to the exponent, minus 7, divide by that. So we get minus 1/7 x to the minus 7. All right, so with that choice of u, dv is forced, which then gives us a du and our v. So let's remember the integration by parts formula. I'll put it up over here. The integral of u dv is equal to uv minus integral of v du. So if we do that here, u times v, that's minus natural log of x over 7x to the 7th. And that's u times v, minus the integral of v du. So that's minus 1/7 x to the minus 7 times 1 over x dx. So this one then becomes plus 1/7 the integral of x to the minus 8. Pull the minus 1/7 out, so minus minus is a plus. And then x to the minus 7th divided by x, using rules of exponents, is x to the minus 8. So the last step then of our integral, we get a minus natural log of x over 7x to the 7th. And then this guy we actually already integrated over here. That gives us a minus 1 over 49 x to the minus 7. And instead of putting on a plus c, we put on our bounds of 1 and 2. And yeah, plug in. All right, so it looks like that Liate served us well. We got ourselves, this worked out because of the way we had u set up. All right, so cool for that one. All right, so let's go back and look at then the next one on the list, which was I guess let's take a peek at number 10. See what's going on there. Okay, so we've got the natural log of 5t plus 8. And this one says use integration by parts again. What tells you should use integration by parts anyway? I mean, other than the fact they tell you to. I guess I would argue the fact that there's only one thing makes it so that integration by parts is really our only choice. But I'm not actually going to do integration by parts with this one, because we already know what the integral is for natural log, right? We already did integration by parts with that. So what I would do is just a u sub. Good old fashioned, let's let u equal 5t plus 8. So du is 5 dt. So that turns this into the integral of 1/5 natural log of u. We know the integral of natural log is u, natural log of u, minus u, plus c. And then, of course, we can plug back our u. So we get 1/5 5t plus 8 natural log of 5t plus 8 minus 5t plus 8. All of that needs to be in brackets, plus c. My guess, Rigney, you said you kept getting the wrong answer. My guess is probably a parenthesis issue of some kind. But
the form I get doing the integration by parts is, it differs from that form that you got. But the form of the original equation is pretty similar.
Okay. Because if it's a natural log, the integral of natural log is x log x minus x. So I don't know what to tell you. Maybe we can look at yours specifically sometime, like maybe at the end of class. But
I didn't even consider trying just a straight U sub. Like, it makes sense. I agree that it's a good strategy. There, in the Canvas, there's like links to videos for specific problems, and I was already kind of on the same wavelength. And I checked out the video. I was like, "Yep, this guy's doing it the hard way. Like, I'm gonna do it the hard way." And with the by parts, and it just, and the form I wound up with looked like the same form that was in the video, but it just rejected me.
All right. Well, maybe I can look at yours specifically, and after class I'll look, because I can look at your individual work and I can see what you put in and what they wanted, and see if I can figure out what the issue is. So.
All right, cool. Yeah, we'll do that.
All right. So that was number 10. So then 12, 13, and 14 is going to be more of the same. All right. So for this guy, we've got sine of minus 3r over e to the 6r. All right. Well, let's go to the whiteboard. Okay, so I'm going to go ahead and clear all this stuff. We'll start fresh. So we're integrating sine of minus 3r over e to the 6r. All right, so if we're going to try this by integration by parts, what are you going to want to pick for your u? What does Liate suggest?
I tried sine first.
All right.
But then I think I messed up.
Okay, I love the idea of starting with sine, because that's the t part of Liate as opposed to the exponential part of Liate. So I would say good choice. All right, so du then is going to be minus 3 cosine of minus 3r. The minus 3 came from the chain rule. And then v, if I integrate this, I'm going to get minus 1/6 e to the minus 6r. Think of this as just e to the minus 6r dr, right? So the e shows up again, and then the minus 1/6 comes from the substitution. So we're going to get here then, if we do u times v, so minus 1/6 sine of minus 3r e to the minus 6r minus the integral of v du. So minus 1/2 the integral of cosine of minus 3r e to the minus 6r. Dr there. But the half was the 3 times 1/6. All right, so this is one that suggests doing u sub again, or sorry, integration by parts again. So if we let u equal cosine of minus 3r, then dv is going to equal, again, the e to the minus 6r dr. All right, so du is going to be 3 sine of minus 3r. And v, again, is going to be a minus 1/6 e to the minus 6r. So if we put that in here, we get minus 1/6 sine minus 3r e to the minus 6r minus 1/2 times u times v. So minus 1/6 cosine of minus 3r e to the minus 6r minus the integral of v du. So that's going to be a plus 1/2 the integral of sine of minus 3r e to the minus 6r dr. Okay, so this then suggests that we need to do another integration by parts, but we're now in that world of we're cycling through. If you look, this is exactly the same as what we started with. So if I do a integration by parts, I'm just back up to here with my u and my dv, which then leads me to another cosine, which then leads me to this integration by parts, right? It's back and forth. So what was the trick here? You remember what we did here when we show up to the same integral?
The resulting exact same one over to the left side of the equation?
Yeah, now we just do some algebra. Because we already had, like, if you come back over here, right, we already had this integral was equal to, think of this as a big equation. Well, this piece that's that same integral, I can move over to the other side. So what I'm going to get is 5/4 the integral of sine of minus 3r over e to the 6r dr is equal to minus 1/6 sine of minus 3r e to the minus 6r plus 1/12 cosine of minus 3r e to the minus 6r. Oops, not xr. All right, so where'd all that come from? So again, hopefully you see these two pieces. That's the minus 1/6 of this, and then the minus 1/2 times minus 1/6 gives me a plus 1/12. But the reason this is 5/4 is if I distribute through, I get minus 1/2 times 1/2, so minus 1/4. I'm going to move that to the other side by adding 1/4. So I have my original 1 plus 1/4 is 5/4. We should definitely have a plus c over here somewhere. And so the last step is going to be to divide by 5/4. So choosing u equals sine of minus 3r is definitely a good route. It just, in this situation, if you ever end up with the same integral that you started with, that's actually a good thing, because then you can do some algebra. All right, so better for 12. All right, so then let's see what 13 has in store. All right, so use integration by parts to evaluate this integral. Okay. So we have sine to the minus 1 of x. All right, well, if we're going to do integration by parts, what are you going to pick your u to be?
So I actually asked about this one, but mine has something in the parentheses. Could you add a number?
Sure. What would you like in there? Do you care?
An 8.
Cool. 8. So sine inverse of 8x?
Yeah, mine's cosine, but like I can figure the opposite out. I just...
Okay. So here's what we're going to do. I'm going to start by doing a u sub. So this becomes 1/8 the integral of sine inverse of u du. Okay, so when you asked to put a number in there, in my mind, I went, okay, because all it does, if all we have is a multiple of x, it's exactly the same as if there isn't anything in there, just multiplied by 1 over that number. Just because that's how the u sub ends up working, right? So don't let that, like, yes, I know it looks completely different. It barely changes anything. Yeah, it barely changes anything at all. Let me, you know what? I'm not going to use u. I'm going to use w because I want to save u and v for the integration by parts. All right, so now for here, let's go to integration by parts. So we're going to have u equals, well, we don't really have much of a choice. Let's just use sine -1 of w. And then dv is going to be dw. Okay, this is one of those situations, kind of like when we did the integral of natural log. That's our choice, right? So our inverse trig function is our choice. All right, so we got to start with the derivative of inverse sine. All right, so who remembers the derivative of inverse sine?
Is it a fraction?
It is a fraction. There is a 1 over.
1 over square root of 1 minus x squared.
Okay, except this time it's going to be w squared. So Adam, you're the u over u squared minus 1. What do you mean by backwards?
So I messed up the sign. I think, isn't it? I think I'm already wrong, but I'm putting in tangent. I'm just wrong. Never mind.
So tangent would be 1 plus u squared on the bottom. Inverse tangent would be 1 plus u squared on the bottom.
No, I'm just all wrong. Never mind.
Okay.
I take it back.
We're all good. All right, so here are our pieces then. So if we put that back into our integral here, I got 1/8. We need u times v, so w sine inverse of w minus the integral of v du. Okay, so now we've got this integral that remains. So how are we going to tackle that integral right here? Don't overthink it. But when we get to about this point is where we really start overthinking integrals, and we think about all the different forms and this, that, and the other thing. Looking at this one, I want you to notice that this is really fast if we just do a u substitution. If we let u equal 1 minus w squared, then du is a minus 2w dw. I already got the w and the dw and even the minus. So I'm only off by that 1/2. So this becomes the integral 1/2, 1 over the square root of u. If you do the u sub, and then that's fast, because that's just u to the minus 1/2. So I think I'm going to leave this one here, because at this point now, you know where to go. But check this one out. I mean, this required basically 2 u subs. There was the original one, and then this other one that popped up, and integration by parts. So this is not uncommon that you have to do multiple types of integration techniques in the same problem. But yeah, so there you go. Alternatively, if you remember the formula for the integral of inverse sine, actually, I don't know if I gave you a list of the integrals of the inverse trig function, but this is basically how you can develop them. All right, so is that good enough shove for this guy? And I know, Alexa, you said you had cosine inverse, but it's same story. It's just different derivative at this point for your u. All right, cool. So let's go see what the next one has in store for us. Number 14. So use integration by parts to evaluate this integral. Oh, goodness. All right, so we've got cosine of natural log of 3x. All right. Well, let's clear all this real quick and see how this one plays out. All right, so we got the integral of cosine of natural log of 3x. All right. So they suggest doing a integration by parts. I'm down with that. And if we're going to do integration by parts, then u is going to have to be the function itself, because that's the only thing we've got. We don't have multiplication. Remember that this cosine, it's not cosine times natural log, it's cosine of natural log. So we really have just the one function, right? All of that is just one function. So when in doubt with the integration by parts, pick that function as your u. So let's differentiate it. Derivative of cosine is a minus sine. And then we need to multiply by the derivative of what's inside. Okay, well, the derivative of natural log is going to be 1 over what's inside times the derivative of what's inside the natural log. Okay, so there's my du. And then v, of course, is just what we started with. All right, so we've got u times v, so x cosine of natural log of 3x minus the integral of v du. All right, well, when I integrate or multiply these together, those 3's reduce, these x's cancel, subtracting a minus is a plus, and we're left with sine of natural log of 3x. That's what we're integrating. All right, so there's our first step. This new integral doesn't actually look any better, but maybe you can see what's going to happen. What's going to happen here when we try integration by parts one more time?
Don't we end up back at the beginning?
Yep, this is going to be another one that brings back the whole integral that we started with kind of deal. So if we let sine equal, or u equal sine of natural log of 3x, and again, dv equals dx. Okay, so du, the only thing that changes in here is instead of minus sign, it becomes a cosine. So cosine of natural log of 3x divided by x dx. And again, v is equal to x. So if I put all that stuff in, x cosine of natural log of 3x plus u times v, x sine of natural log of 3x minus the integral of v du. Okay, so we're at that same kind of place as we've seen before, where this is the same as what we started with. So we can bring that over to the other side, do a little bit of algebra, and you're good to go. So this one actually ends up being just the same as I think the first one we looked at, that led to the same integral showing up again. All right, well, that's not a problem. We slap it onto the other side, do some algebra. This one we're just going to end up having to divide by 2. So anyway, hopefully that's a good enough shove for this one. And for your specific one, it might be a little bit different. But the fact that it's a cosine, that's what led to, you'll see that a lot with cosines and sines. Not always, but frequently when they are part of your integration by parts, you end up with the same thing that you started with. Again, it's the nature of sine and cosine, right? All right, so there's that guy. And by my count, that was all the ones that people asked from 3.1. So let me go look at the one point from 3.2. And the one qualifier I'm going to put on this one, I forget who asked. I think it might have been Alexi. We might not have talked about how to do this specific one yet. And if we haven't, I'm going to wait until I show you some more examples, because we're kind of in the middle of 3.2 right now. So 3.2, number 13. Yep, we're going to wait on this.
Oh, I totally meant 2.9. Sorry.
Okay. And then let's go look at 2.9. All right, so then this one we definitely should have talked about because hyperbolics. So let's take a look at number 13. Did we look at this one? Maybe not. That's all right. Let's see. So we've got x cosh inverse of x over 4 minus the square root of x squared minus 16. And we want f prime of 9. All right. Let me clear all this garbage. Start fresh. All right, so we've got f of x equals x cosh inverse of x over 4 minus the square root of x squared minus 16. And you're looking for f prime of 9. All right, so basically we just find the derivative and plug it in. I really feel like we did this one before. That's all good. So derivatives, no integrals, just derivatives, right? We're just differentiating now. So this is x times cosh inverse of x over 4. So that means we need the product rule. All right, so the product rule on that, think about what we have to do for product rule. We multiply the derivative of one times the other. All right, so the derivative of x is nice and easy. That's just 1. Hold on a second. Where am I? There's my whiteboard. Okay, so we get 1 times cosh inverse of x over 4. And then we add to that x times the derivative of cosh inverse of x over 4. So cosh inverse, its derivative was 1 over the square root of that thing squared minus 1. but now we have to do the chain rule, multiply by the derivative of x over 4, which is 1/4. So that's the product rule on this piece. So now we get to take care of the minus square root. All right, well, that's x squared minus 16 to the 1/2. So we get 1/2 times x squared minus 16 to the minus 1/2. And then from the chain rule on that, multiplying by the derivative of what's inside is 2x. So this was that piece. And now plug in 9. Right? So this is the other issue that I think we start running into now is we're so in integral mode. Or just integrate, that we forget to do the simple things sometimes. So don't make life harder than it needs to be. Just go back to what you know. All right, so there you go. There's a little bit from the homeworks and all that. All right, so I'm going to go ahead and jump up to the whiteboard and show you more trig integration. Like last time, it's going to be identity heavy, and I know that doesn't that a lot of people are not super into that. But this is why we do trig before we do calculus. All right, because it's a great tool. Anyway, so I'm going to hop up to the whiteboard and I'll be back with you in just 1 second. All right, so last time I showed you how we deal with powers of sine and cosine when one of them is odd. And basically the trick is when you've got one that's odd, you reserve one for your du from the u substitution, and you let u equal the other one. All right, so it's actually kind of a nice little trick when we've got sines and cosines. But that only works when we've got one of the powers being odd. And so the question is, what do we do if both powers are even? So let me show you an example. And in fact, what we're going to do is let's look at one where we only have one trig function. All right, so let's look at this guy. Let's say I just wanted you to integrate cosine to the 4th of x. So even if you wanted to, like we did before, where you go, okay, let's reserve one of them and replace the other, there is no other, right? We only have cosine to the 4th. All right, so here's what you're going to have to do if all you have are even powers. You're going to make use of the power reduction identities. And so I put those up on the board last time. I'm just going to put up the one for cosine squared right now. Cosine squared of x as a power reduction, it's 1/2 times 1 plus cosine of 2x. So we're going to make use of this whenever you have an even power, or only even powers. You're going to make use of this. Just watch what happens. Cosine to the 4th. This, of course, is the same as cosine squared times cosine squared. And what I can do is I can replace both of those with this power reduction. So I'm going to get the integral of 1/2 times 1 plus cosine of 2x times 1/2 1 plus cosine of 2x. Those 1/2s I can bring out front as a 1/4. And then if I FOIL this out, if I actually multiply that out, I get 1 plus 2 cosines of 2x plus cosine squared of 2x. So up to this point, we haven't touched calculus, right? We did a trig identity swap, and then we did some algebra. But I want you to start thinking what's going to happen when we do calculus. Looking at this form, I want you to notice some things. First of all, the 1, no problem. I can integrate that, no issue. 2 cosine 2x, similarly, no problem, right? That's just a real quick u sub, and I've got that integral. And then I've got cosine squared of 2x. All right, well, cosine squared of 2x, that's a similar issue. We've got an even power of cosine, but notice that that power is smaller than what we started with. By using this power reduction, we've reduced the power down. All right, well, that's good. Because for us integrating, we don't want powers, right? We just want a power of 1. We don't want these bigger things. So we're definitely on the right track. But I still have this square I want to deal with. Well, all I'm going to do is this power reduction again. I'm going to use power reduction so that I don't have a square anymore. And so this is what that's going to look like. Let me see if I can make this fit. So we're going to have 1/4, 1 plus 2 cosine of 2x. So those two pieces, we'll just leave them alone. But now here's what comes from the power reduction on cosine squared of 2x. That's going to be 1/2 times 1 plus cosine of 4x. Now I want to pause for a second, make sure you guys are all good with where that 4x comes from. Because sometimes this throws people. You go, wait a minute, it should be a 2x. But what we're doing here when we do power reduction is we're doubling the angle. Right? Whatever the angle was in here gets doubled from power reduction. And right now, the angle is 2x. So I have to double that, turn into a 4x. Okay, so we got rid of that power. Let's see what this looks like now. So we've got 1/4, the integral of, if I distribute through, I'm going to get 1 plus 1/2, that's 3 halves, plus 2 cosine of 2x, and then I also have a 1/2 cosine of 4x. All right. So again, 0 calculus has been done. Right? No calculus whatsoever. But now we're ready to do the calculus. 3 halves, no problem. 2 cosine 2x, that's just a u sub. 1/2 cosine of 4x, also just a u sub. All right, so this is why we do identities. Right? Just plain and simple. The reason that we make you do all that identity shit for like months in Trig is because it's an incredible tool. If you had Trig with me, I know I told you many times, oh, you'll see where this is useful in calculus. This is where this is useful in calculus. Because now the integration is easy. Here we go. We're going to get the 1/4 times 3 has x. The 2 cosine of 2x, that's just a sine of 2x. And then when we do the 1/2 cosine of 4x, that's going to be 1/8 sine of 4x plus c. So there's your integral of cosine to the fourth of x. Obviously, we can do other identities and change the form on this if we want, but I don't want. I'm going to go ahead and just leave it like that. Okay, so the moral of the story here is that when you have even powers, and only even powers, you have to make use of power reduction. Okay, so the power reduction identities are going to be kind of big here. All right, so with powers of sine and cosine, we're good. We really see that they're the two techniques, right? Either save one for use of or use power reduction. And you might have to do both through the process of power reduction. You might get to a bit where you've got sines times cosines, and all right, fine. But this is the general process. All right, so yay, we now know how to deal with powers of sine and cosine. Well, the reason that we were able to do the tricks for sine and cosine is because of the Pythagorean identity. It really all comes back to the good old sine squared plus cosine squared equals 1. So that means that if we can do that trick with sines and cosines, we should also be able to do the same thing with secants and tangents. Because you may remember that there was the form for the secants and tangents. In terms of the Pythagorean, there was this guy, tangent squared plus 1 equals secant squared. So we're going to be able to tackle the same kind of thing if we've got tangent to the, I forget what powers I used before, to the k times secant to the h. Okay. So what if we're in this situation? Well, because of this identity, so that form of the Pythagorean, we're kind of in the same boat where depending on the form, we can make use of things like u substitution and all that to convert it into something that's pretty easy. Okay, but now this one we got to think a little bit more though, because the derivatives of tangent and secant are not each other, right? So like tangent, we know that the derivative of tangent was secant squared, and the derivative of secant was secant tangent. So if we're going to do a u substitution of any kind, we need these things present. All right, so we either need 2 secants available or 1 secant and 1 tangent. So here are the 2 main cases for this form. The first one is going to be where secant has an even power. So I call that H. We're going to go where secant is even. If this is the case, what we're going to do is we're going to reserve 2 of them for u prime. And we're going to let u equal tangent. The other big case is going to be where tangent is odd, so where k is odd. And in this case, we're going to reserve 1 tangent and 1 secant for u prime. And we're going to let u equal secant. Now you might be saying, okay, well, what do I do if I don't, if both of them, you know, if h is odd and k is even? You can actually get to one of these forms using identities. But these are the two general cases. So let me show you some examples. And you'll see that it's not that terrible. It's just, you know, the process. It's just what we got to do. Okay, so let me start with a case 1 where we've got an even power on secant. So keep the Pythagorean up there because we're going to want to make use of that. But let's say we're doing this. We're going to look at the integral of, let's just go tangent squared secant squared. Now, let's go secant to the 4th. Secant squared is too easy. Okay, so this is case 1, where we have h is even. So we're going to do a u substitution. We're going to let u equal tangent of x. So then du is secant squared x dx. All right, so watch what happens when we do that. This now becomes the integral of u squared, tangent u squared. I'm going to have secant squared times du. I'll keep that black. We'll keep all the x's black. All right, so here's why it's still a secant squared. We had 4 of them, right? Secant to the 4th. 2 of them were incorporated into the du, which leaves us 2 more. All right, so that's great and all, but we still have secant squared x. We got to get rid of the x. Well, this is where our identity is going to come in. I can turn that secant squared into a tangent squared plus 1. And now I can substitute in for that tangent. We originally had our u was equal to tangent. So this becomes u squared times u squared plus 1 du. So notice what happened. By letting u equaling tangent, we were able to adjust everything else so that we're now just in terms of u. So let's finish this one off real fast. This is the integral of u to the 4th plus u squared. So that's u to the 5 over 5 plus u cubed over 3. And then we substitute back in our u. So we get tangent to the 5th over 5 plus tangent cubed over 3. And that, ladies and gentlemen, is the integral of tangent squared secant to the 4th. You can check yourself as always. If you just do the derivative of this thing, you'll probably have to use some identities and stuff, but it will simplify down tangent squared times secant to the 4th. Okay, so when the power on the secant is even, this is the route that you want to take. All right, so then what about if we don't have that, but we have an odd power on tangent? well, let me show you one of those, and you'll see that it's really kind of the same idea. But before I go there, we good? Questions on this one? So it's all pattern recognition. It's all looking at what's our form to do it. All right, so let me show you the other case where we've got an odd on the tangent. So let's look at this guy. Let's look at the integral of, let's say, tangent to the fifth, and then we'll go say secant cubed. So we'll even make them both odd. So we have tangent to the fifth secant cubed. All right, so now we're going to do u substitution again, but this time I'm going to let u equal secant. So then du is a secant times a tangent. So here's how this integral is going to start looking when we start changing it. So I'm going to start with my du. The du is going to take one of the secants and one of the tangents. So that's going to leave behind 4 tangents and 2 secants. But the 2 secants are going to be u squared. So if you look at the bits that are in red here, this is 2 secants and a secant and a tangent. So that's a total of 3 secants and 1 tangent, which leaves me tangent to the 4th. All right, so we're on our way, but we still have to replace that tangent to the 4th. And that's where we're going to use the Pythagorean identity, because if we solve this for tangent squared, that's secant squared minus 1. And tangent to the 4th, this is tangent squared squared. So what this integral is going to look like now is we're going to have secant squared minus 1 squared times u squared du. And then now we'll replace our secant squared. So this is u squared minus 1 squared times u squared d. So that was a whole bunch of trig and algebra. I mean, we did the one step of calculus with the use of it, but that was it. But I want you to notice now what we've got is an integral that's just a polynomial. If we FOIL this all out, you multiply everything out and all that good stuff. We're just integrating u to the 6th minus 2u to the 4th plus u squared. And now that it comes time for calculus, that's fast and easy. So this is u to the 7th over 7 minus 2u to the 5th over 5 plus u cubed over 3 plus c. And of course, we need to put back in our u equaling secant. So this is secant to the 7th over 7 minus 2 secant to the 5th over 5 plus secant cubed over 3 plus c. So I know it's not pretty, but think like a mathematician. Mathematicians are all about, can I do it? Can I get the answer? Yes. Yes, I can. Here it is. All right. Okay, so with tangents and secants, just like with sines and cosines, you can convert them into nice forms because of that Pythagorean identity. Same trick happens with if you've got cosecants and cotangents. I'm not going to show you any because it's like identical to tangents and secants. But anytime you have those pairs together, you can pull a similar trick. All right, so these are integration tricks, techniques that come from the Pythagorean identity. But there are some other identities that were kind of big in terms of making things easier to integrate. And the next ones I'm going to talk about are an identity that you probably don't even remember. Like, and I don't mean like remember what the identity actually says, but maybe not even remember that they are identities. They were a set that are called the product to sum and sum to products. I don't know if that rings a bell for anybody, but what they are, let me show you real quick. We're going to look specifically at the sum to product to sum. So this is what they look like. The first one was when you had sine times sine, so sine of alpha times sine of beta. This ended up being 1/2 times the cosine of alpha minus beta minus the cosine of alpha plus beta. Similarly, there's one for sine times cosine. It's 1/2 sine of alpha minus beta plus sine of alpha plus beta. And then there was also one for cosine of alpha times cosine of beta. And that's 1/2 cosine of alpha minus beta plus cosine of alpha plus. So I put these up on the board, and some of you are probably like, whoa, I don't even remember this at all. And that's okay. Where they come from is by using the sum and difference of angles identities and just kind of fiddling with them. But these are called product to sum. When I teach trig and we get to these identities, these are usually like the last ones we see. So people are already kind of burnt out. And they don't really have application out in the real world. But they have huge application to calculus. And I think that's one of the reasons why most people don't remember them as they go through trig, because they were at the end and you don't use them. And if you're told anything, like I'm sure I said, trust me, you're going to like these when you get to integration. And at that point you went, yeah, okay, he's talking about some weird thing, and this is next year's problem. But let me show you why this is really, really nice if we're integrating. So suppose, just as an example, let's say we had this integral. I wanted to integrate, say, sine of 3x times sine of 5x. Okay, so no big deal. Just going to integrate sine 3x times sine 5x. So you see the multiplication, and your brain should go to integrate by parts. It will, your brain will get there. That when you have multiplication, the first thing you should think is integration by parts. However, if we use identities, we can actually turn this into an easier form that's not going to require integration by parts. The other thing that should make you really leery about doing this with integration by parts is the fact we've got sines or cosines, and we've already seen that that tends to be cyclical, and those things can get kind of gnarly. All right, but check this out. Go to the first identity. So we're going to get a 1/2 that I'm just going to pull out in front of the integral. But look at what we're going to get. We're going to get the cosine of the diff of these angles. So 5x minus 3x is 2x. And then I'm going to subtract the cosine of the sum of the angles. All right, so this was just using the strictly just jumping straight to this product to sum identity and putting it in. But now I want you to notice that we've got a difference of things that we're integrating. Oh, that's easy enough. You just integrate each one separately. And each of these just requires a u sub. And that should make you happy. I don't know, does it? U sub is easy, especially compared to like integration by parts. So using these product to sums, turn these things into forms that are super fast. All right, so like if I actually finish this one off, what I'm going to get is the 1/2, that's out front. The cosine of 2x is going to give me a 1/2 sine of 2x. The cosine of 8x gives me a 1/8 cosine of 8x. And there you go. There is the integral of sine of 3x times sine of 5x. All right, so the moral of the story here is that even the often overlooked identities can actually be really handy when it comes to integrating. Basically, here's what we're doing. We are trading out integration work. Yeah, yes, thank you. They are both sine. I don't know why my brain did that. But basically, we're trading out trig and algebra for calculus. And trig and algebra are supposedly easy. So we're doing these easier things. We're doing this work to change our form into one where the integration is easy. All right. If you don't want to do this, that's fine. Do integration by parts. Have fun with that. It works. It's just going to take you a lot longer. And yeah. All right. Anyway, so here's another set of identities that, believe it or not, are going to be useful when they show up. There are other forms that lead to the same kind of thing. The double angle identity is a good one too. Remember sine of 2x, it's equal to 2 sine x cosine x. That's another one that can be useful because you can take the sine times cosine and turn it into one thing. But like I mentioned before, this one, it all comes down to how good is your trig. And the weaker your trig, the harder these sections are going to be. Sorry. But anyway, trig integrals. Depending upon what your form is, you can make use of all kinds of different identities. Now, this is where those of you that don't like trig are really not going to like calculus. Because here's another great technique that we can do. Depending on the form of your function, you can have a function that has no trig in it whatsoever. But if we substitute in with trig, things get nice and easy. Let me just start off with a super easy example of a function that we want to integrate. So this one's not bad at all, right? This is just, I want to integrate the square root of 1 minus x squared. And if you were to say, okay, well, whatever, this is some bogus whatever. This is actually the graph of a semicircle. So if we go back to an area example and I say, okay, I want to find area of some portion of a semicircle, that's this guy. All right. So it's not even a crazy function. It's the top half of the unit circle. So it's a pretty common function. But if I were to ask you to integrate this, find an antiderivative, you're going to look at me and go, well, we could try u substitution. But if we let u be the inside, the du has a minus 2x. Don't have that on the outside, so that's not very good. And then you might go, well, maybe we try some sort of like integration by parts thing. Yeah, you could try that. Again, not so useful. But let me show you a trick. Here's what I'm going to do. This came from the unit circle, right? If you think of this as y equals the square root of 1 minus x squared, which of course, when you rewrite it, that's your unit circle. You may recall that with the unit circle, there's a relationship between that and, say, trig functions. So what we know about all of this is that this 1 minus x squared, that kind of comes from Pythagorean identity and suggests this as a possible substitution. So here's what we're going to do. We're going to substitute in, just go with me on this for a second. Let's substitute in for x. And I'm going to let x be the sine of theta. Now, this is a little bit backwards. You're used to doing some sort of a u substitution, so u equals in terms of x, or theta equals in terms of x. This time, we're going to let x equal something in terms of this other function. So again, just go with me here for a second. So if we differentiate that, the derivative of sine is cosine of theta d theta. Let's plug that stuff back in. So we're going to get the integral of the square root of 1 minus sine squared theta times cosine theta d theta. Okay, so this is what it looks like if we do the substitution. Well, let's simplify. 1 minus sine squared is actually cosine squared. That comes from the Pythagorean identity. The square root of cosine squared is cosine. So by doing this substitution, I now have the integral of cosine squared d theta. So it probably felt like a really weird substitution to do. You know, like x equals sine theta. But notice that by doing that, it brings us to a form that we know how to tackle. That's what we were just talking about, right? Powers of sines and cosines and secants and cosecants and stuff like that. All right, well, let's keep going with this integral. So this substitution was great. It got us here. But now to do this cosine squared, we need to make use of power reduction. I'm just going to write our substitution up here. All right, so if we do the power reduction on this one, remember cosine squared, it's 1/2. Integral 1 plus cosine of 2 theta. And this one we can do. So we're going to get 1/2 plus 1/4 sine of 2 theta plus c. All right, cool. This weird ass substitution of x equals sine of theta got us to a point where we could integrate. But we're not done. You see what we have to do now? What do we still have to do at this point?
Get that back in terms of x.
Yeah, we got to get back in terms of x. We started with x, we got to end with x. So we got to replace again. Okay, so we need to somehow change this back into x's using x equals sine theta. Well, that's kind of hard. This is a 2 theta, this is a 1 theta. So we're going to make use of trig again. We're going to use another identity. And this time we're going to use the double angle identity for sine. So what I did right there, sine of 2 theta, and then that guy right there, that's just the double angle identity. Now, the reason that that's even helpful is now that sine of theta can become an x. So if I start replacing this stuff, I'm going to have 1/2 plus 1/2 x times cosine of theta. So we're close. We just now have to replace the cosine, knowing the sine. All right. Well, here's how this plays out. We're going to draw a right triangle, generic right triangle. And I want you to think about our substitution. We had that the sine of theta was equal to x. Think of that as a fraction, x over 1. And knowing what we know about sine, sine was opposite over hypotenuse. So that would suggest in our little triangle here that these sides are 1 and x. Okay, well, that's great. But what I really want is I want cosine of theta. I need to replace in the cosine of theta. Cosine of theta is adjacent over hypotenuse. So I need to know the length of this side right here. Well, let's use our Pythagorean theorem. Question mark squared plus x squared is equal to 1. So question mark squared is 1 minus x squared. So the question mark is square root of 1 minus x squared. So that's the length of this side right here. Square root of 1 minus x squared. So the cosine of theta is equal to the square root of 1 minus x squared over 1. So that's how I'm going to replace this guy. And so there's the integral of the square root of 1 minus x squared. Seemingly nice little function. It's just the unit circle. led to some pretty gnarly algebra and trig stuff to get us to a point where we can actually find its integral. Okay, so this is called trig substitution because we're substituting in for x a trig function. So like I said, if your trig's a little weak, this is going to be a challenge. But we taught you all of this in trig in various places. We showed you the identities, like the double angle identity. We did this sort of thing. I don't know if when I drew that picture, maybe hopefully it triggered a little bit of, oh yeah. You did that when you did composition with inverse trig functions. So if you want to go back and look, it's during that bit. Because if we know one trig value, we can actually find the others. You can use identities as well, but I find that the picture is a little bit easier with the triangle. Okay, so, yep, good stuff, right? Sorry, it triggered. That was pretty good. All right, so here's the question. When is trig sub going to be useful? I mean, yeah, it worked out here. But what was it about this form that suggested using trig sub? Well, this is another pattern recognition-y kind of thing. So let me give you the when you're going to use trig sub, what forms you want to use trig sub on, so you can recognize it. All right, so here are some forms. If you have square root of a squared minus x squared, and this form doesn't have to be just itself, like we just did this as its own integral, but you could have like, you know, x squared over this. You could have this times x. You could have, you know, something like that. If you have this form, you want to go with the substitution x equals a sine of theta. So that's what we did with the example I just showed you. A was equal to 1. We just did a sine theta. All right, so again, the reason that you do that is because if you look at the square root, and we substitute in, you can factor out an a. You get a times the square root of 1 minus sine squared, which just becomes a cosine. So if you're in this form, or have this form, and you use the substitution, that thing always turns into an a cosine, which then we should be able to do algebra and trig and stuff to simplify to turn it into a nice integral form. All right, the other forms where trig sub works, you can have a square root of a squared plus x squared. And in this case, you're going to actually substitute with a tangent, a times tangent. Now, if you substitute there, this form is going to look like a squared plus a squared tangent squared. Again, factor out the a. We have the square root of 1 plus tangent squared, which from the Pythagorean is going to turn into a times secant. All right, so we've got a square root of a squared plus x squared. You're going to want to do a trig sub. And then the last form is going to be where you have the square root of x squared minus a squared. And this one, you're going to want to go with secant. We'll go with x equals a secant. And it's really from the same identity as the one before. This gives you a squared secant squared minus a squared, which is a times secant squared minus 1. And secant squared minus 1 is tangent squared. Square root of that is tangent, blah, blah, blah. We got a tangent there. Okay, so trig forms are square roots of sums and differences of squares. When those things show up, trig substitution is a viable option. It's not always the option you want, because sometimes there are faster things to do. Use sub. Maybe it's already the form of an inverse trig function, or whatever. So watch for those. But when you've got these forms, trig substitution can definitely help you. So let's do just one more example before we call it a day. We'll definitely do more of these on Monday. But let's try this guy. Let's look at I want to leave this up here for just a second so we can figure out which form we want to use. Well, let's say we've got the integral of 1 minus x squared, or square root of 1 minus x squared over x to the 4th. Okay, so we look at the different forms. We see the square root with difference of squares, and we settle in on this guy right here. So the trig sub that we want to do for this guy, we're going to let x equal 1 sine of theta. Square root of 1 is 1. All right, so it's totally, this form is what drives my substitution choice. All right, so let's see what happens when we do that. So I'm going to bring that over here. Again, the dx is a cosine of theta, d theta. So what we're going to get is cosine of theta over sine to the 4th theta times cosine theta d theta. So look at where all the pieces came from. The cosine theta d theta, that was our dx. The sine to the 4th, that's on the bottom, that was our x to the 4th. And then our cosine, that was on top, that was the square root of 1 minus x squared. Right? When we've got that form and we substitute sine, it always turns into cosine. All right, so this is now cosine squared over sine to the 4th d theta. All right. So is this any better? What are we going to do now? thoughts, ideas, suggestions? Try a little bit. Well, how about we do this? I'm going to use some trig to break this apart because I don't like having the cosine over sine. I'd rather have something different. So how about we do this? Let's do cosine squared over sine squared times 1 over sine squared. Because then I can rewrite this as cotangent squared times cosecant squared. Does that help?
It condenses it, but then we still have to get back to x. So I think we would still require.
Don't worry about that just yet. We'll get back to x when we need to. Let's just think about integrating this. Can you integrate this? Do you see a process to integrate that?
Yeah, it's possible.
Yeah, it's just u sub actually. If you let u equal, or right here, if we let u equal cotangent, the derivative of cotangent is minus cosecant squared. So this thing becomes the integral of minus u squared. The cotangent squared is the u squared. The cosecant d theta becomes the minus du. And this is easy. So by doing the trig sub, it got us to a point where we could do u sub. Again, combined techniques. But we got our integral. But now comes the fun part. Let's sub everything back. So the u was cotangent. So this is minus cotangent cubed theta over 3. But now we got to get back to x. All right, well, if you remember, the original substitution was x was equal to sine of theta. If we go back to our picture, those sides were length x and 1, and the other one from the Pythagorean theorem was 1 minus x squared. But what I need is cotangent of this angle. All right, so cotangent is the reciprocal of tangent. Tangent was opposite over hypotenuse, so cotangent is going to be 1 minus x squared over x. So I'm going to put that back in over here. And so what we end up for our integral when everything is said and done is minus 1/3 times the square root of 1 minus x squared over x cubed plus c. So, this integral right here, there it is. There's the antiderivative for that function. All right, so it's at about this point that you're all like, okay, I'm done. I don't care about calculus anymore. I don't want to deal with this anymore. And I don't blame you. Because trig sub, there's a lot to it. There's a ton to it. and is bringing back all these horrible things. I don't remember who wrote it, but yeah, you're getting triggered again. You're having these horrible flashbacks to Trig. Me personally, I think this is beautiful. I do. I think this is elegant. It's incredible to me that you can take something like that, but by making use of trigonometry, you can twist it around and mold it and turn it into a form that is easily integrable. And this is about as easy an integral that there exists. It just required a lot of work to get there. And then we had to get ourselves back. Anyway, so this is trig sub. We're going to see more of this. We'll definitely do some more on Monday. But this is another big application whenever you have one of those three forms. All right, so on that happy note, we'll call it a day. Just in terms of things to be aware of, our next exam is 2 weeks from today, giving you the heads up on that. In terms of how far it's going to go, I know it's going to go at least through trig sub. It might include, or it will definitely include a couple more sections. I'm not sure, but I just want to put that on your radar. You know, it's still 2 weeks away, but remember this there. Other than that, there's homework that are due Monday night at midnight. I don't remember if trig sub is one of them. If it is, I'm going to change that date. And I'll also take care of the fact that there appear to be 2 quizzes next week. I'll get everything shuffled. But anyway, so I guess though with that, hey, have a good weekend. Don't stress too much about this. It'll come the more you practice it. And yeah, so have a good weekend. And I will see you in March. Can't believe it, but Monday's gonna be March 1st. So have an awesome weekend, and I will see everybody then. And you're welcome, guys.